Welcome to another computer lesson. This time we're reminding you about step functions. This is just a reminder because I know you did these last year, so we'll make this a quick one. So step functions, that's the street lingo. Step functions. In the math classroom, we generally refer to these things as the greatest integer function. Step functions are basically anything that look like stair steps, and the most popular of them all would be the greatest integer function. And you recognize that you're dealing with the greatest integer function by a double-barred bracket. Let's jump in and just see what we're talking about. Basically, what we want to see when you see this symbol for a step function is we want to know what is the greatest integer. Remember the integers. We don't include fractions. We don't include irrational numbers. The integers are basically the whole numbers and their negative counterparts. But when you see this symbol, we want to know what is the greatest integer on the number line that has been reached by that number. Let's dive in. You can follow along in your notes. These are right there. So for example, what's the greatest integer function of 2? Well, this is not that hard. But if we go and we look at our number line at where 2 is, it's right there. And what's the greatest integer we've actually reached? Well, remember, to get greater on a number line, we move from left to right. And the greatest integer we've reached is, well, we've reached 2. Well, that was boring and was not challenging. Greatest integer functions really flex their muscles with fractions. So let's take a look at this fraction here, 2/3. So if I come over here to this number line and I graph 2/3, it's well, about right there. What's the greatest integer that we've actually reached? Well, have we actually reached 1? No. No, it's not a rounding function. We haven't reached 1. The greatest integer we have reached is 0. So why don't you try the next one on your own? Why don't you try finding what the greatest integer function of 5 1/8 is? Well, hopefully you thought on a number line 5 1/8. We've gone slightly beyond 5. We haven't reached 6, so it's 5. And let's just do one more problem just to make sure you really have it. So we're at -3 1/8. -3 1/8, I hope you said the greatest integer function is -4. Oh, I bet you missed that one. Students always miss this one. Negatives throw kids off. Remember, this is not a truncating function. It's not one that just throws away the fraction. It's the greatest integer that you've reached. -3 1/8 is right about there. Have we actually reached -3? No. The greatest integer we have reached, though, is -4. Okay, let's dive in and see what this graph looks like. So here we go. The parent function, y equals the greatest integer function of x. Well, when in doubt for graphing, just start plugging and chugging. Let's put in 0 for x. When x is 0, what's y? Well, it's 0. That's right there. What about when x is 1? Y is 1. When x is 2, y is 2. When x is 3, y is 3. As a matter of fact, when x is -1, -2, -3, this looks like it's a linear graph. But it is not. Remember, greatest integer functions really flex their muscles with fractions. So let's take a fraction. What happens when x is a half? Well, when x is a half, y is still 0. What about when x is 3/4? When x is 3/4, y is still 0. As a matter of fact, y stays 0 this whole time until we reach 1. And at 1, we're going to jump up. And we're going to stay here this whole time until x becomes 2. And so you can see as we extrapolate backwards here, this is called a step function. It looks like stair steps. So let's dive in and take a look at how we can shift and scale these step functions. And I'm going to just go ahead and I'm just going to launch into one of the messiest ones we can do. I've got numbers all over the place. This is not on your homework, but just watch and see what happens. Like all parent functions, the first thing I'm going to do is I'm going to find out where the new origin is. So let's take a look at the horizontal shift. We're going to use the same trick we always do. We're going to set what's inside the function equal to 0 and solve it. And that tells me we're going to shift left 2. As as the vertical shift, we can see right here, it's simply up 1. So left 2 and up 1, this is our new origin, and step functions will always start, always start with a solid circle at the origin. Now, all other functions, I like to make a table of parent values, but step functions, I think we could just logic our way through them. Let's talk about what's happening to this step right here. Normally, this step would go to the right and end with an open circle. And then we jump up 1, it'd go to the right and end with an open circle. However, we do have some horizontal scaling with this 1/2. Do you think this half means that we're going to go to the right a half? No, it's inside the function. And as we learned in class just yesterday, anytime you're inside the function, things behave opposite. The horizontal scaling is 2. So I'm actually going to go to the right 2. And that's the length of my stair. We sometimes call this the run. The run is 2 units. Now, typically, I'd go up 1 and I'd start my new step. But we do have some vertical scaling here. The vertical scaling is 3. So where this step ended, I'm going to go up 3 and start my new step with a run of 2. And you could keep going, although we run out of space, so let's extrapolate backwards and go down 3, run of 2. That is how you transform step functions. You've got some problems to try on your own, logic your way through those, and see how you do. Have them done by the next time we meet. Have a good day.